ferromagnet, so net angular momentum is 0, then they showed that, okay, there is no Sturmian Hall effect. So our collaborator in Kyoto University, Teru Ono, tested this idea using the ferromagnet, so gadolinium cobalt iron cobalt platinum layer. And the first they checked the DMI field, that is this amount, which is much larger than the hard existence field, meaning that we would have well-defined topological charge Q, and also measure the velocity field ribbon, and the maximum velocity was obtained at 280 K, meaning that this is the angular momentum compensation temperature of this sample. And they fabricated a really complicated device, and this zoom-in image here, this is current line. There are half circle shape. So when they inject current, it generates vortex field which concentrate at this semicircle region in one direction, depending on the current direction. And they tried to nucleate magnetic bubble or magnetic fermion. So here is the mock image. They already injected the current, and you see that there are some less dark region. This is the reverse domain compared to the other areas. And then they inject current through the platinum layer in order to apply the spin orbital. Then they observed, oh, this bubble is elongated along one direction. Actually, the student who did the experiment was disappointed, because actually he first expected that, oh, this bubble will move, but actually the bubble doesn't move. It just was elongated because very strong pinning around here. During the device fabrication, there are some strong pinning sites may arise, and then his bubble cannot show the isolated motion, instead just elongation. And then we asked him, okay, let's reverse all the magnetization direction. So he did it, and then he found, again, this bubble is elongated, but in a same angle in terms of the magnitude with the opposite sign, which means that this bubble is topological, because when you reverse of the all magnetization direction, your topological charge changes each sign. Okay? So, and then he repeats the same measurement at various temperatures. For this temperature, angle is negative. For this temperature, angle is positive. At this temperature, angle is more or less 0. So all the results are summarized here. Magnetization off state, blue, magnetization down state, red. This is the this angle. And he found that this angle becomes 0 at 280 K, which is the angular momentum compensation point of this ferromagnet. So it is in agreement with our expectation. We also carried out the atomistic LLG equation and varied the net angular momentum, and we calculated this elongation angle. So this is negative, this is positive at TA is more or less 0, and the results are summarized here. So this is also consistent with experiment. Okay, I have 10 more pages. So spin drift diffusion model is very useful theory to interpret your experimental result, especially for the spin orbital measurement. And actually, it originates from the GMR, giant magnetic resistance, to explain this. Simple idea to explain the GMR is the two current model. So you have a different scattering, so different resistance for the upspin and downspin depending on the magnetic configuration. Equivalent circuit is here. For upspin, both layers are up, so both are small magnetic resistance, but downspin both are large resistance, and net resistance is given here. When you make the antiparallel configuration for both spin up and down, one is the small r, the other one is the large r, and so on and so on, then you can calculate the net resistance, and you can find that if small r is smaller than large r, then parallel resistance must be smaller than the anti-parallel resistance. That difference gives you a GMR. However, this is good to explain, however, it is not very accurate because we ignore the spin flip scattering. So actually this is not two separate spin channels. There are always intertwined channels in many places. Then you have to go to the Boltzmann type equation, including all this scattering. So Ballet and Ford theory, they started from the Boltzmann equation and they used several approximations and arrived at this drift diffusion equation. So spin drift equation is spin current is proportional to the spin conductivity and also the gradient of the spin chemical potential. And spin diffusion is given by this equation. So by incorporating these two equations, you can include the spin flip scattering, which is characterized by this L sub s, which is the spin flip length. Here is an example. So here I solve the spin drift equation for the normal metal ferromagnet, normal metal trilayers, and here I assume boundary conditions, spin accumulation is 0 here and there. And you see that spin accumulation is positive left-hand side of the ferromagnet, negative right-hand side, and spin current is maximized near the ferromagnet and it decays exponentially because of the spin flip scattering. You can do the same thing for the spin barrel with two ferromagnets, and depending on the magnetic configuration, you see the spin accumulation pattern is different. So spin accumulation is proportional to the spin chemical potential, salt chemical potential, meaning that you have different resistance if chemical potential profile is different. And then is spin transport torque. Okay, I can skip here. Also skip here. I want to finish within 1 hour. Okay. So, okay, I have to explain this. So, this is the free electron Fermi surface in the momentum space. Now you apply electric field, then we know that Fermi surface is shifted. So this spin corresponding to this state, meaning that describes the electron state propagating along the x direction. So it is first polarized by this ferromagnet, so its spin direction is up, then enters into the right ferromagnet, so it experiences the exchange torque, so it precesses in the space. So when I draw this component in the space, it just precesses for the one electron if I ignore any relaxation. However, we have not only this state, but also that state, meaning that electron moving in that direction. So because of the kx projection of this red state is smaller than the black one, meaning that the wavelength becomes a little bit longer. So you have this precession. Then you have also the green state, longer precession, and or blue state, much longer precession. So when you have to calculate for this transverse spin current configuration, the distribution within the right ferromagnet is you calculate all kind of these wave patterns for all state on the Fermi surface and sum up. Okay, then the result is this one. Because a very significant out of phase, it quickly goes to 0. And this length scale is called the ferromagnetic or spin current length. It is usually very short. It is not 0, but we assume, okay, it's 0. Then you can obtain this famous boundary condition for the spin current, which include the spin mixing conductance G up down, rear part, and here I ignore the imaginary part. And this term appears in both spin transport torque and the spin pumping. And they are related through the Onsager relation. So by combining this boundary condition with previously explained the spin drift diffusion model, then you can calculate the spin torque angular dependence in any kinds of a metallic structure. So it can be complicated, and because here we have 3 ferromagnet layers. Okay, so the next one is a very brief one, band structure calculation, which becomes more and more important to understand the spin-orbit effect. For the spin-orbital, spin-Hall effect, and nowadays the orbital Hall effect, orbital current, and so on. Actually, I need 2 more hours to explain this, so I don't do that. Well established. There are various ways and various code you can use. If you learn manual correctly, you can use it correctly. But one thing that I want to emphasize is that this band structure calculation is not always correct. Actually, it is based on some assumptions, so it is not first principle actually. But anyway, you can calculate band structure, and then if you know the band structure and eigenstate, then you can perform the transport calculation. Usually we calculate the conductivity. So this is spintronics related. So we are interested in the spinor conductivity, for example. Then you use the Kubo formula shown here, where this capital omega is the so-called spin vary phase, spin vary curvature. And using this equation, you can calculate the conductivity. This is an example of a ferromagnet. So depending on the x to z, g to minus y rotation of your magnetization, we could calculate the conductivity or current, spin current. So then you can identify, oh, there is Alvan Hall effect contribution, there is also the planar Hall contribution, and so on and so on. Okay, this is the end of the first part. Thank you for your attention, and I would be glad to have questions.
Actually, it may be a very basic question, but when this at the angular compensation temperature, this cobalt gadolinium thing, how they exactly like compensate net angular moment? I mean, their rotation may be in opposite direction, but what about the magnitude? I mean, what is happening at that particular temperature? So there.
Okay, so in equilibrium, we can just calculate the magnitude of cobalt spin and gadolinium spin and calculate the net spin and or net magnetic moment, right? It's easy. During the dynamics, you have to go to the atomistic energy. They don't compensate. They can generate some additional magnetic moment and so on, but it is because of the dynamics. Okay. Did I answer your question?
No, actually, no. Like I want to know what is like because when we talk about magnetic compensation, we can say like their net magnetic moment is in opposite direction, it is getting compensated. But like about this dynamics, how exactly the dynamics is like, let's say this gadolinium angular moment is in this direction and cobalt is in opposite direction. But how like magnitude is getting cancelled at that temperature?
So gadolinium moment, cobalt moment.
Yes.
So by summing up these two, then they are cancelled.
Okay, maybe I can discuss it later. So the second question is that to measure this angular compensation temperature, apart from this dynamics experiment, is there any other experiment by that we can get that this is the TA for this particular material or like ferromagnet?
To my understanding, this is the easiest experiment to measure that. You can use more difficult measurement to define the angular momentum compensation point, but it's more difficult. You can measure the rotation angle, rotation sense of your spin wave. It changes at the angular momentum compensation point when you cross this point, but it's much more difficult measurement.
Okay.
So I would suggest to use this field-driven domain of motion measurement.
Okay. Has anyone did something related to the other experiment? I mean, apart from this dynamic measurement, has anybody tried to measure this temperature by any other experiment?
So you can vary the temperature for one sample and measure the domain velocity that I have shown.
Yes.
So, yeah.
Thank you.
Maybe I have missed the point. How you have calculated the spin accumulation from non-magnet and ferromagnet and non-magnet?
Oh. I'm sorry, I don't have a detailed equation here, but from this equation, you put this term to here, then you can find that the second derivative of mu s is given by mu s over length scale square, meaning that the general solution is exponential function. So you have a exponential plus b exponential minus. So depending on the layers, you have two unknowns for each layers. And at the boundaries and also the left and right boundary of whole sample, you have boundary condition. That gives exactly the same number of equation, just as the number of unknowns. Then you can algebraically solve those equations to get the A and B, and then you can plot this one.
Thank you.
And that is well explained in this paper.
You said we couldn't use a continuous approximation for antiferromagnets or ferromagnets, but why is it the case? I didn't really get why.
If you want to use the continuum approximation, which means that within a unit cell you have uniform magnetization. However, for antiferromagnetic equilibrium magnetization is 0, and it becomes very small some number during the dynamics, but it is non-uniform within the cell. So there is no way to calculate the antiferromagnetic dynamics using the continuum model.
So it's impossible to have like 0.1 nanometer unit cell, it wouldn't make sense even.
I would say no, so you have to use really atomic descriptions.
So hopefully a quick follow-up to that then. So what about in the case of DMI? Because there you've, in the unit, I think if I get it right, in the unit cell you have, your spins are canted at your sites. So does the continuum approximation hold for that when doing a micromagnetic simulation, or do you need to do atomistic modeling in order to really accurately do DMI in scalyonic simulations?
Yeah, if you want to be very accurate, then you have to use atomistic LLG equation. Even though DMI can make a canted magnetic moment, it actually, that magnitude changes during the dynamics. So if you don't use atomistic LLG, then you have to use very crude approximation about that magnitude that would give an incorrect result.
Okay, thanks.
You want to take 5, or yeah, so let's take 5 and then come back a little bit later, and then Kyung-Jin will, Professor Lee will continue for his second part.